Let's try to continue. I hope you had a good break. Who checked out the systems in the back? Are they fun? What's the most fun system you found?
The Cray.
The Cray. Very nice. There's more than one Cray. Where's the other one?
CN or is it C?
Yeah, in the connector on the side. Cool.
Sorry, I had a question about the Morse law from before. So, what was the internet like in 88?
Slow. In one word. Crappy in another word.
So did it have like
Not public in a third word. So this was like in 88, it was mostly a research network between the US military and a couple of universities. I think they had some international lines already. So the Europeans were connected and Asians as well, but only very limited, as far as I remember. But you would have to look up the history of that. I'm not 100% sure. It was very, very slow, so you had a couple of lines, think kilobits, and sending an email with a couple of words was taking minutes to send from one system to another. Usually people logged in from their home computers, which were like Commodores or very crappy systems, to their university system to like check their emails. So phone line to university system, not over the internet, to log in and have a remote session on a computer there. It was a shared multi-computer that just hosted email pretty much. Like the early emails of the days was mostly email and running some programs for the nerdier folks.
But the damage was like, wouldn't be as catastrophic today.
Correct. Yeah. Like so the damage, like the internet went down for a couple of days, but yeah, it's as if your email, your postal mail got delayed by a day or two. You don't care, right? Like I think it's the inverse about postal mail. Like it's the same situation as we handle postal mail today, right? So we don't care if who still gets postal mail, right? It's
The Swiss government.
the Swiss government. They send you love letters every year, end of January, and they ask you for money. Yeah.
How did it find its targets?
Say again?
How did it find its targets to affect?
How did it start? Right. So the person the Morris.
No. How did it find its targets to?
How did it find its targets?
Because
Not-
there was no NAT, so I
Right.
didn't use local network. Did it
For
just
I in all addresses do connect. Right. 2 lines of code. Just flooding the network. I'm not 100% sure. It's been a while since I looked at the code. I think it also parsed the host lists. Right. Most of these systems had a host list of nearby computers, so you can connect through those. So it was one part.
Was it really necessary to privilege escalate every machine on the internet in order to like count them? I mean, I guess there was no ICMP or.
Well, it was a teenager, right? That wrote the worm. Oh, it's just a fun project. No, it was not necessary, right? There were maps that said like these are all the computers, and back then you could have 1, 2, 3, 4, 200, right? And you're done. There were a couple of hundred machines, or a couple of thousand machines, not a couple of billion machines as there are today. Right. Other questions? Yep.
Did Morris face legal issues like water fraud charges or?
There were some, but most of the hacking laws were actually only created after the Morris worm. Right, so all of the wire fraud charges, all the heavy legislation only happened after the Morris worm took over. So he ruined the fun for all of us. Other questions? Cool, then let's continue. Software engineering versus security. Software engineering aims for dependability, productivity, usability, maintainability, and everything else you have learned in your software engineering course. Software engineering looks at the aspects of PL, networking, project management, economics, human resources, and so on. From a software engineering perspective, security is often secondary. It's like a thing that you do on the side. Right? Yes, like people are aware we need to do some form of security, but there's other stuff that can happen. And security from the software engineering side is often limited to testing, and software engineering generally ignores mitigations such as different kind of deployed mitigations per se. Yeah.
Shouldn't availability also be there?
For software engineering?
It's kind of usability, isn't it?
Yeah.
Okay.
If your system goes down every 2 minutes, it's not like, as I'm saying, right, this is not, it's the next slide. Right, so these are just some of the major components. This is not a software engineering course, and I'll get to that slide in a bit. But what is security, right? Security is this abstract thing. And we need to define what we mean by security to be able to develop policies, to be able to test security, to be able to measure security. And security as a definition is the application and enforcement of policies through mechanisms over data and resources. So this gives us quite a couple of things to hold on to. So security is the application and enforcement of policies. So this gives us security properties. Through mechanisms. Mechanisms is how we enforce a given policy. For example, an implementation or an instance of a policy. So the policy could be, for example, memory safety, right? Security is the application and enforcement of memory safety. And so, e.g., memory safety, okay? Through mechanisms over data and resources. Mechanism to enforce memory safety could be compiler based. So for example, softbound, which is a compiler that enforces memory safety for C or C++. It could be language based. For example, through C-cured, which is a C dialect that enforces memory safety. Or Rust, or Java, or whatever, right? So there's different ways to enforce a given policy. And security is the application and enforcement of a policy through a mechanism over data and resources. And the data and resources are then what you protect. Security best practices that we have from other classes that you should already know: always lock your screen, unique per service passwords, use two-factor authentication, encrypt your transport layer through TLS, messages through GPG, file systems through dmcrypt, disable password logins on SSH, open any unknown executables in an isolated environment. Yes?
Is if you see a QR code in a commercial, is it a bad idea to open it?
Do you want to enlighten us about the background of that?
So during the Super Bowl, which is which is a football game that takes place every year,
Which they play with hand eggs.
because you carry the ball on foot, that's why it's called that.
Exactly.
And so there was an ad from a crypto company called Coinbase, which was just a QR code bouncing on the screen. The idea was people would scan it and then open the link in the browser.
Right.
And there was controversy about whether or not this was secure.
So, for those on the recording as well, I just figured out I have to repeat it, because otherwise it's not going to be recorded. The question was, can you scan arbitrary QR codes, or can you open arbitrary URLs? And the question was centered around a lot of InfoSec drama. Information security people are a very peculiar group of people, and they like drama. Most of the drama happens on Twitter. So you can follow me on Twitter to get some of that drama, which is sometimes fun. Sometimes there's flame wars, sometimes there's discussion, but there's usually a lot of drama. The most recent drama was after the American Super Bowl, which is mostly about watching commercials for whatever it's worth, where one of the commercials asked people to open a URL in a browser. And the InfoSec drama around that was that, hey, you cannot have people arbitrarily click on URLs. This is going to be so dangerous, and people could have taken over their system. Now, we'll get to that in a bit when we talk about threat modeling and other aspects. There's layers to it. If you put your security hat on and you join in on this discussion, there's several layers to that you can think about. One of them is, yes, this could be an attack that somebody wants to run an exploit on your system. There could be a bug in Chrome, and we've just seen like 15, 20 minutes ago that Chrome had 14,000 bugs. For sure, in these 100 million lines of code, there's going to be a couple of thousand more bugs that are left that will be exploitable. So this URL that people opened could have contained a 0-day that would have pwned all the systems. Sure, that's possible. Now let's discuss, as we're doing threat modeling, what the possible options and downsides here are. And if you think about it, the web or the browser, the idea of using a browser is to encapsulate, and JavaScript allows the attacker to run arbitrary code in your machine in a contained and constrained environment. So you cannot, in theory, it cannot access any arbitrary resources on your system. So that's the security that the browser gives you. So when you are entering a URL by hand or by clicking on a Google search result, you assume that by entering and browsing to this URL, you're safe, right? And the whole idea of the last 30 years of browser security was to make it as safe as possible to open arbitrary URLs. Because you generally don't trust the internet. Like anything on the internet could be bad and inject, like trigger a 0-day bug on your system, right? So the InfoSec community was right that yes, this could be an entry vector that triggers a bug on your system and then takes over your system. Sure, because there will be bugs, right? Now, that's one side, and that resulted in the drama because people said, OMG, right, you shouldn't click on arbitrary links, this is so dangerous. Then, on the other hand, like, this is the insanity side of the people. On the other hand, there were a whole bunch of other people that tried to look at this a little bit more objectively and then discuss what are the actual effects. And if you are, how is this different compared to your regular browsing behavior? Like all of you are entering URLs by hand. All of you are maybe scanning a QR code somewhere. You will be looking at, you'll be clicking on a link on Google or Bing. It's your choice, I don't judge, right? You can use any kind of, or DuckDuckGo, right? Any kind of search engine. You'll be clicking on those links. That's also a link that is being sent to you, right? So in the end, the attack or the attack vector is similar. Right? You're clicking on links. That's what the web is here for. It's just another form of link. Right? It's just it could be by email, it could be by whatever. Right? It's just a link in the end. Now, so this is the risk is similar to clicking on any other link that you will see. So there's no accelerated risk. There's no need for drama there. Now let's talk about the goals of the attacker. The attacker must have a certain set of goals, right? The attacker wants to do something. Usually, if you are like a nation state, the NSA, or the Russian, or the Chinese, or the Israeli Secret Service wants to extract some data from you, and they figure out you have exactly the data I want. So they buy an exploit. An exploit is $100,000 to $1 million US. They customize the exploit, they slap a little bit of code in, and then they run it on your system. If they do that, there's no way you can do it, right? They will just get your data, right? Because they know there's always bugs in there. But there's a price tag to it, right? It's $1 million to clone your system. So the Secret Service must know that the data that they are getting is at least worth $1 million or more. Because there's a price tag attached to it. At the end, it's a market. It's economics 101, right? Like there's a price tag to getting that data. Now, running a Super Bowl commercial costs a couple of million US dollars.
7 million it cost them.
7?
7 million.
So in this example, it was 7 million US dollars.
For 30
So,
seconds.
so they must have spent 7 million US dollars to run the ad, another million US dollars or two to create the exploit, so there would be 8, 9 million US dollars, and then they would pwn a whole bunch of systems. Now there's two different kinds of attacks, right? The targeted attack to get a certain piece of data where I know that's the data. Or the other attack where I just use all your GPUs to mine cryptocurrency. Right? Because you get code execution. And if you pwn one person, it's highly unlikely that this person will notice. If you pwn 50 million people, it's very highly likely that a whole bunch of people will notice and there will be reactive measures to that. So, who would pay from an economical perspective? I round up $10 million US dollars to get access to 50 million GPUs for a couple of hours, because the attack would be noticed after that. Go ahead.
Probably also be forced to pay reparations.
Right. There's a money trail to it, right? There's the you could do plausible deniability. Oh, we were hacked. This was not our URL, whatnot, right? But there may be legal repercussions and whatnot. And you would get access to a couple of GPUs for a couple of hours, right? You get much more GPU power if you just like get a couple of machines on Amazon or on the Google Compute platform. Right, so from an economical perspective, from an attacker perspective, it makes no sense whatsoever to run an attack that way. Does that answer your question?
Yeah.
So it's it was a fun discussion. It was a fun drama. It was an interesting thought experiment. But if you do the threat modeling, you see that it actually does not make sense. Right? Who would pay that much money to, in the end, get access to a couple of machines? Right? And you only get access to these machines for a very short amount of time. Because if you're attacking millions of people, hundreds to thousands of people will notice. And then this will become public and people will run reactive measures. Now, so this is interesting threat modeling here. Let's move on. Let's pop a couple of frames from the stack. Let's continue with software security. So we talked about security best practices. Software security is the area of computer security that focuses on testing, evaluating, improving, enforcing, and proving the security of software. And we'll cover these pieces in more detail as we go along. Now, why is software security so difficult? There's a human factor to it. The programmer, the software architect, the designer. Maybe the programmer had a bad day. She didn't sleep well, or he didn't get his second cup of coffee. Right? There can be many different issues. So they were not concentrating enough. There's a bug added. The designer missed some aspects of how you were interacting with another component that resulted in the bug. And the issue here is, right, the attacker may only be, or an attacker may only be looking for a weakest link, right? The attacker only needs to find one bug. One exploitable bug is enough. And there's this disparity between attacker and defender. The attacker needs one bug to exploit your system. You, as the defender, you need to stop all attacks. So the big difference here is, as an attacker, you are working on it exists one bug, and you're good, right? There exists one bug. And as a defender, you do this for all secure, right? So you, as an attacker, you have to prove there exists one. As a defender, you have to prove for all code the security properties hold. Now, if you've done any kind of constraint analysis, any kind of logic, any kind of proving, you know that proving this one is much easier than proving this one. Right? Because here in the second one, as a defender, you have to show that no single bug can exist. Like either the negation or the for all code. As an attacker, you only have to show that, hey, there's this bug. I can exploit it. This gives me a root show. I'm done. Right? So this makes this harder for the defenders. In addition to that, nobody likes to pay for security in different angles, right? Security or security measures can cost you performance. If you do run additional security checks, if you check if this pointer is null, then I do something else. This is additional cycles that you're executing on your system. This is costing you energy. This is costing you time. Right? So you want to minimize the amount of security checks from an engineering perspective. There could also be usability. Like security can be a pain to work with. Like figuring out a new password for each service, this is annoying, right? I just want to reuse the same password everywhere and be done with it. Right? So this is hard. Also lack of resources. Security is only, like you only figure out that you missed it after you have been exploited. Right? Or after all your hard drives have been encrypted with malware. And then you figure out, oh, I should have invested more into security. But it's only after the fact, after things have gone wrong, that you figure this out. What are some of the security best practices? Properly design software, have clear documentation, leverage frameworks, as in don't re-implement all the functionality that you need. Like if there's a library for it, use that library. Do code reviews, add rigorous security tests to unit tests, formal verification for components that can be verified, extensive testing for all other components. Red team software, offer bug bounties. None of these are done in practice. All of these are nice to have. So a lot of this is best effort, right? So these are security best practices, and we are working towards increasing these best practices and making sure that we get more of these covered. It's also a rather new field, right? So many of the developers never had a security class, right? So I graduated from ETH in 2006. There was no single security class in the curriculum. That was 17, 16 years ago, right? So the security classes are very, very new. And you're likely working until you're 65, right? So there's a lot of developers out there that never had security classes. And this takes time to actually get this rolled out into production. I've talked a lot about bugs. What exactly are software bugs? Software bugs are errors, flaws, failures, or faults in a computer program or system that causes it to produce an incorrect or unexpected result or to behave in unintended ways. Bugs arise from mistakes made by people in either a program's source code or its design in frameworks and operating systems and by compilers. This is very fuzzy, right? A bug is something that violates the specification that you have in principle. Now, if people are not doing any of this, do we think they write a formal specification that you can test against? This is going to be very hard, right? So finding or deciding if something is a bug or a feature is already challenging in the first place, and then isolating it and making sure that you can detect and argue that this is a bug that needs to be fixed is another point. That's why if you're looking at bug bounty programs, It's easiest if you can demonstrate, hey, through this bug, I get a root shell. And as a famous hacker once said, you can't argue against the root shell, right? If you demonstrate that this bug is exploitable, then they will have to fix it. So this is a very powerful tool that you can use as a security analyst if you want to. Some common bugs, spatial memory safety, is if you do have a buffer, you keep iterating through that buffer, and the pointer PTR suddenly points after the end of the buffer. If you access that buffer, there's a spatial memory safety violation. Freeing an underlying buffer or returning and accessing the data on another stack frame is a temporal memory safety violation. Those should be pretty standard, just as a refresher. Another common bug type that is getting more and more common, this is one of the nastiest types of bugs in Google Chrome that have resulted in a lot of payouts, is type safety violation, like type confusion. How's your C++, folks? Are you fluent or beginners? Fluent, so, beginners. Who has programmed in C++ before? Wow, amazing. More than half. Cool. So C++ is just like C with a little bit more types, but no additional guarantees. And in the end, you can cast between different classes. So there's an object hierarchy. There's a type lattice. Like different classes are related to each other. We've got a parent class and two types of child classes. You can cast an object from a child class to the parent class. This is called an upcast. And you can cast from a parent class to the child class. This is called a downcast. And we have a base class, that's the parent, and greeter and exec, which both extend the base class. And then we do a cast from greeter class, from a greeter class to an exec class, which will then result in the type confusion. There's going to be more example on this later because it's quite intricate. I just wanted to introduce it today. Software vulnerability could be, for example, one of the three types of issues that we've seen before. Is a software weakness that allows an attacker to exploit a software bug. So all the vulnerabilities are bugs, but not all the bugs are vulnerabilities. Depending on what your security goals are, a bug may not be a vulnerability. It could just be it computes the wrong result, or it just doesn't do anything bad. A vulnerability requires three components. The system is susceptible to the flaw, right? The system needs to have this underlying bug. The adversary has access to the flaw. So for example, if you're looking for a remote attacker, but the bug can only be triggered by a local user, then it's not a vulnerability. And the adversary has the capability to exploit the flaw. So the adversary knows to massage the heap, for example. Like it could be the second point is that the adversary can reach the bug and trigger the bug. The third one is that the adversary can set up the environment in a way so that the adversary's goals are achieved. For example, if the adversary wants to have code execution, but it only crashes the system, then the adversary does not achieve their goal. One of the big issues that we have here when we're working with low-level languages is a set of broken abstractions. So let's say Alice is working with her nice and beautiful high-level code up there, and she's working with these Lego bricks, which is super cool, right? You can work with types, you can work with abstractions, and you know what you're working on. But if a coworker, Bob, made a stupid mistake with the function pointer, and there's a buffer overflow there, where some other piece of code could violate it. So there's no bug in here in this example itself, but there's a function pointer being used, right? And the function pointer being dereferenced. Now, at the C or C++ level, you can argue about high-level types. You can argue about function prototypes and so on. At the assembly level, all you see are assembly instructions. As soon as you violate the high-level abstractions, as soon as the bug is being triggered, you exit this beautiful C++ world and start executing in an ugly world that we are calling a weird machine, and different kind of abstractions will hold. Right? And here, this is it's just the assembly instructions that the CPU executes, and all the type information and so on no longer matters. And we'll cover more of this also later, and how these abstractions actually matter. Because in the end, it's like pieces of data that are organized in different ways that are fed into assembly instructions. And you no longer care about the high-level code at the C or C++ language level. In the end, you just look at code snippets and how you can connect these code snippets to make them do whatever you do. For example, your code snippet may be expecting a linked list, right? So you may be iterating through a linked list. Now the attacker can just reference that, like the linked list becomes a tree or like a interconnected list. Like the list loops back on itself. And the code will just happily execute and continue. So this is the difference in abstraction that can happen. So the original code, your list API, may never allow the creation of such illegal lists. But an attacker that exploits a memory safety flaw can overwrite one of the pointers so that the list loops back on itself, for example. Right, and thereby abuse these abstractions. Now, this is one of the things that we'll discuss in the course, among several others. Software running on current systems is exploited by attackers, despite many deployed defense mechanisms and mitigations, and even best practices for software development. The goal is that at the end of the course, you will understand state-of-the-art software attacks and defenses across all the layers of the abstraction, from the machine code side up to programming languages. So programming languages, compilers, runtime systems, CPU, ISA, as well as operating systems. And then the course will allow you to connect across these different parts. And this is also precisely what fascinates me so much about security, and especially systems and software security. Instead of just focusing on one layer, like if I would be just a systems person, I would be working on operating systems. If I would be just a compilers person, I would be working on language or language design, right? Like in most other fields, you're focusing on one niche, on one layer of abstraction. But security allows you to cross-cut all the different abstractions. And violating assumptions in one layer of abstraction gives you additional privileges in another layer of abstraction. And that's the fun part about security. With a question?
What is ISA?
ISA, instruction set architecture, like RISC-V,
okay.
RM.
Yeah. ISA are an architecture, yeah. Like the different kind of machine code instructions there are, or how the machine code instructions are set up. x86 is an ISA, AArch64 is an ISA, RISC-V is an ISA. Learning outcomes: understand causes of common weaknesses, identify security threats, risks, and attack vectors, reason how such problems can be avoided, evaluate and assess current security best practices and defense mechanisms for current systems, become aware of limitations of existing defense mechanisms and how to avoid them, identify security problems in source code and binaries. This is also the first lab that we will start this Thursday. It's code review, finding bugs, understanding kind of simple bugs, and then writing some unit tests, and then assess the security of given source code. We have 4 parts. We start with part 0. This is the basics, the first 2 weeks. What are threat models, confidentiality, integrity, availability, and so on. And also secure software lifecycle, a little bit of software engineering. Then we'll come to the fun part. Policies and attacks. What are core security policies? Compartmentalization, isolation, memory safety, type safety. Bug as a violation of a security policy, and what are common bug types that then result in vulnerabilities. Then different kind of attack vectors. how they tie together, what's a confused deputy, what's control for hijacking, code injection, code reuse, or information leakage. This is also where we'll start the CTF, where you can actually apply all these different angles and figure out how they tie together, and then practice them. Because you can listen to me talk for hours, but you have to try them out yourself to figure out how they work and how they actually connect together. Second part, stopping exploitation, or part 2, stopping exploitation. We'll talk about mitigations and existing mitigations, and some more advanced mitigations that are on the verge of being deployed. So there's more and more mitigations coming around. Some systems already have them. If you have Androids, a lot of them already come with shadow stacks, which we have actually worked on. So this is actually currently being deployed on real systems. This is kind of cool. Makes your systems more secure, but they have not been deployed widely yet. Third part, finding bugs. This is mostly focusing on discovering and finding as many bugs as possible, enabling developers to fix them afterwards. And then we'll end the course with a couple of case studies on browser security, web security, and mobile security. Course material. The slides and discussion will be on Moodle. You can ask questions there, as I said earlier. Do register. If you cannot register for the class, shoot me an email and I will register you. So I've heard some PhD students and some students may have a hard time registering because it's Moodle. It's a crappy piece of software. There's a couple of complementing books. I recommend 20 Acres Operating System Security, which is a nice orthogonal security book that covers how to secure underlying system. You can download the PDF for free from this URL. And the Operating System 3 Easy Pieces book. That's also available freely. The textbook you can download from my homepage there as well. And in addition to the course, we'll have labs and exercises for you to work on it. The textbook will focus mostly on the software security principles, policies, and protection. When I originally designed this class, there were no textbooks. There are still no good textbooks. So my book so far is in the form of a script. It's about 150 pages or so. And I've gone through a couple of revisions. It's still an early beta, so I consider all of you beta testers. If you do find bugs, issues, or things that are not explained clearly enough, let me know and I'll update. I'll usually go through the chapters a couple of days before the class and then update them accordingly. If anything, as I said, is not done well enough, do let me know and I'll happily expand it. Also, if you find typos, sentences that are not clear, and so on. This is work in progress, right? But I'm trying to do this as a service for you, so that you have something in addition to the slides to hold on to that summarizes all the material. Feedback is very much encouraged. For this semester, my goal will be to mostly rework the testing section, so there will be heavy changes on the testing section, and some minor changes in the earlier sections to just update the material and make it more current. We'll have 3 labs focusing on different aspects of software security. The first lab will be coding practices and code review, starting this Thursday for the first 30% of the lab points. This is just to get you a bit more familiar with C, C++ coding, the different lab environments, submitting. Based on feedback from last year, we'll do a submission that will be not graded in 2 weeks to give you feedback. So for a lot of students last year, it was very hard to figure out, have you found the right amount of bugs? Did you find the right issues? Is the format correct? So we'll do an intermediate submission after 2 weeks, where you will get feedback, but that will not be graded. So we'll try to do this for the other labs as well. The second lab will be adversarial testing. This will be in the form of a CTF, so you have 2 weeks to solve a certain amount of challenges, but it's going to be a bit inverse. Usually in a CTF, the harder the challenge, the more points it is worth. Now, this generally does not work in a class environment, because like in the end, 80 or 90% will pass the class. Now, if only 2% can solve the hard challenges that give most of the points, the distribution will be very, very skewed, right? So some people will have 10 times as many points than the majority of others. So we've adjusted the points that simpler challenges give you most of the points, and the harder challenges just give you few points. So if you want to get a passing grade, you just do the simple challenges. If you want the top grade, you can do some of the very advanced challenges as well. This will also limit the amount of time that you have to invest into the CTF. So we don't expect you to just do this class and no other class. In addition to that, I'm very much aware that you have 30 ECTS credits, and this is just 6 credits of this. So there's a lot of other classes you'll be focusing on in addition to that. Third lab, automated testing, which will be another 4 weeks. The largest, heaviest lab, where you're going to apply a lot of different techniques to find security bugs. TA support, we've got 3 TAs assigned and a student AE. Ahmad, who is working on network protocol fuzzing and state inference. Andres, who's working on compartmentalization and security abstractions. And Luca, who's doing a lot of binary analysis in his spare time. Luca is also one of the very, very avid CTF players that you can reach out to. Scheduling, live lectures each Tuesday, exercise sessions Thursdays, ask questions on demand, and the goal for you should be to read the material of the book to prepare. Slides will be on Monday. Slides will be on Moodle before the class. Recordings after the class. Grading. The lab assignment, the 3 labs will give you 40% of the points. We'll have 3 quizzes in addition to that. These are short intermediary quizzes. Think of this as mini exams. They are there's going to be a Moodle quiz that is open for 30-ish hours, and you've got 30 minutes to solve those. The goal there is not to make these super, super heavy, but so that you can get like a good look over the material. And this gives me, this helps you and forces you to read the different sections in the book, and prepares you better for the other parts. Right? Every time we switch from one area to another, we'll have a quick save point where you can run where we'll do the quiz on basics and policies, mitigations and testing. We'll just timestamp and let you work on those. The final will be the remaining 50% of the grade, and this will be on the last week of the class. If you do have scheduling issues, let me know early and shoot me an email for that. Feedback and questions. Use Moodle for concrete class or lab questions. Join the exercise sessions for one-on-one help and hand-holding. If you're struggling, let us know. I am very much aware how busy student life is. If you are struggling with the class, with the labs, with anything else, let us know early. If there's any kind of issues, just shoot me an email. Please let me know. If you wait until the class is over, there's very little we can do. So I'm very open towards feedback. If there are issues, do speak up. I will not hold this against you. In fact, I will actually reward you for that by adjusting and changing and trying to accommodate and help as much as I can. Right? We are in this together, and we're trying to make this a fun class, both for you and for me, right? So that we can all enjoy it together. So direct and frequent feedback is very much encouraged. A note on ethics. Thinking about that, I just declined supervising a master thesis where a company asked to develop a RAT, a remote administration tool. I have to bring up the ethics concerns, right, that we all have to face. There's different aspects to that, right? You learn skills that can be used for good and for bad. And there's different shades of grays in software security. Right, so you can use the skills that you learn in this class to go ahead and find bugs in code, and then go ahead and pwn the other students in this class. You can try to pwn my machine. You can try to use this to gain information, which of course is illegal. Right, so this would be the black hat approach. There's the gray hat approach, so you can look out for your own profit, and there's the white hat approach where you try to be honest and professional about it. This is a piece of shit. We only have like 10 more minutes, but that's okay. I hope it survives that long. For those on the recording, the screen, the projector just showed up that there's a temperature alert. So assume you find a security bug in a broadly used system. What do? Well, you can put on your black hat. You exploit the vulnerability and steal information because you can sell the information on the black market, which gives you likely the most money, but it also comes with additional risks, right? This is, on one hand, this is highly illegal. On the other hand, depending on how much money you take, you may have to run, right? You can go full disclosure, so you release all information publicly. This is kind of an not so fun move, because then the company will struggle to find it. Or you disclose responsibly. So you work with the vendor on a fix and hope for a form of a bug bounty. Note that this is a technical course and not an ethics course. So you are responsible for your actions, and I'm not legally responsible for what you do with these skills. Academic integrity. All work that you submit in this course must be your own. Unauthorized group efforts are considered academic dishonesty and will be reported. You are allowed to discuss the problem with your peers. Copying code, even in part, is not allowed. If we suspect that you've been copying code, one of the things that worked reasonably well in the past was that we invite you for an interview, and you have to justify your code. If you cannot justify your code, the interview will then replace the points in the lab that how you scored in the interview will replace the points you would have gotten in the lab. Right, so if you do suspect that there's fraud, it's one of the measures we can do, but we'll also report them upwards. It's a very ugly, it's a very long process. I had to go through this a couple of times. It usually breaks my heart. It breaks my heart every time I have to do it. It takes weeks out of my schedule. It's super annoying, and it also sucks for you as the student. So cheating is not worth it. It's not fun. You will be likely caught, and try to start. Like if you start the labs early, if you come to the exercise sessions, there's no need for you to cheat. The labs are all very much doable, right? So it doesn't make sense to exchange information. If you do copy and paste code, for example, from Stack Overflow, to just like add a comment, yes, this code is from Stack Overflow. This is perfectly fine, as long as you say that, yes, I copied this from Stack Overflow. We will use automatic tools to compare your solution, and we've set up a system that automatically does that. So we'll regularly find people doing it. This is very, very unfortunate, and unfortunately very, very common. So this is just a reminder for you to not do that. This was all for today, and I'll leave you with a Hack the Planet. Who has seen the movie Hackers? Just one. Oh no. Like, so you know, as an additional exercise for this weekend, fire up Netflix, or if it's available there, or your whatever search engine that you use, and go watch Hackers. It's an amazing 90s movie. It's super cheesy, but very, very fun to watch. It held up pretty well. The only thing that's a bit unrealistic is that they are skating everywhere. So do watch it. It's a super fun movie. So summary for today. Software security is the area of computer science that focuses on testing, evaluating, improving, enforcing, and proving the security of software. Goals for this class are to learn to identify common security threats, risks and attack vectors for software systems, assess current security best practices and defense mechanism for current software systems, design and evaluate secure software, and overall have fun together during the labs. Are there any questions? Going once, going twice. So thank you, folks. Have a great day, and see you next week. Oh, or on Thursday for the labs, of course.